Okay, now that we've explored a little bit about sample means and the fact that the central limit basically tells us that if we sample enough of a, let's say, population distribution of any shape or form, the more we sample it, we will actually arrive to something that looks like a normal distribution. Well, since we have this theorem that basically guarantees that everything will look normal once we sample enough, we can actually generate some statistics and calculate probabilities associated with different features of the distribution. So what is the likelihood or the probability will be under a certain value, or what is the probability will be able to collect another sample that has a characteristic of being above a certain value. So that's what we're going to investigate in this particular problem. Let's go ahead and read through this example here. We have a human resource consulting survey, and this survey randomly selected 60 twin city construction companies to find information on the cost of their healthcare plans. One of the items being tracked is the annual deductible that employees must pay. The Minnesota Department of Labor reports that historically, the mean deductible amount per employee is $502 with a standard deviation of $100. Okay, there's four things that we want to calculate in terms of a probability. Compute the standard error of the sample mean for the human resource consulting. We'll need that to calculate the probabilities. What is the chance the HRC finds a sample mean between the values of 477 and 527? Calculate the likelihood that the sample mean is going to be between another range of values. And finally, what is the probability the sample mean is greater than a certain value? Okay, so let's go ahead and open up the starting file and start solving these problems. Okay, let's start investigating this particular problem and document what we know. We do know, in fact, that the mu, the average deductible, was 502. So let's go ahead and document this in our spreadsheet. The first thing we need to calculate is going to be equal to, or I should say, the first thing we need to calculate is the standard error. We actually have another set of information in this problem that's relevant. So let's not just stop at 502. Let's actually go ahead and document the standard deviation. I'm going to just write that as population standard deviation, and that is going to be 100. We have the sample size n as 60, so we have all of these values to work with. This is basically explaining the shape of our distribution. So let's go ahead and take a look at the first part here. Compute the standard error. So this is part A. So find standard SE, standard error. So what do we need? Well, we need to know the formula for standard error. And I'm going to bring in the formula sheet that has been provided to you. The standard error is defined by sigma x bar. That's basically telling us that it's the sample mean divided by the variation divided by square root n, or sample size. So the mean of the distribution of sample means will be exactly equal to the population mean if we are able to select all possible samples of the same size given the population. Okay, so essentially what this is doing for us is calculating that sample mean variation. So essentially the population standard deviation divided by square root n, and we have both of those values in our spreadsheet. Okay, so the sigma, let's just call it the SE, and let's see, instead of saying find SE, let's just write SE. SE is going to be equal to the population standard deviation divided by square root SQRT of n. and we have a value there of 12.9. Okay, so that is the very first thing we need to calculate when we're dealing with trying to find the probability of obtaining a sample with these desired ranges. Okay, so that is part A. Let's move on to part B. What is the chance HRC finds a sample mean between two values? What I'm going to call this is X bar 1 at a lower value of 477, and then an X bar 2 at 527. And this is going to be used to calculate the desired parameter. But let's look at the formula sheet just a little bit so I can describe what the probability is we're calculating. Okay, so once we scroll through the formula sheet, we have essentially two parameters, two standardized scores that we could consider. One is when we know a lot about the population or the sample mean in terms of the observations. Usually this is selected if you have samples, but you have samples of at least 30 observations, or quite frankly, if you know that it's the population. Our sample size is 60, so we're going to use the Z population. If we have less samples, let's say less than 30, we tend to use the T distribution. That's the biggest difference. But if you are specifically told that you know the population parameter, we always select the Z. Okay, so that's how we're going to essentially calculate the standardized scores that we need to calculate the probability. Okay, so just to bring some background into this, if we were to choose the wrong distribution type, the Z distribution, which is very well defined and essentially does not have a lot of area along the tails in comparison to the T distribution, the less we know about a sample, the more willing we are to place more weight on the sample tails. So anyway, this is just a graphic showing that if N, our sample size, is smaller than 30, we have something that looks more rounded than a bell shape. The closer we get to a sample size of 30, the more that this T distribution is basically forming this nice bell-shaped curve, this distribution. So anyway, that relates to how we're going to calculate probabilities. If we know the population standard deviation, we're going to use the Z. Or if our sample sizes are so big, it's actually not going to matter whether we use the normal .dist formula in Excel or the t.dist, the T distribution. So we're actually up in this portion of the table, specifically calculating probabilities for Z and T distributions for sampled means, i.e. X bar. That's not to be confused with the table above, and I apologize for the scrolling, but the table above here where we're calculating probabilities for Z distributions for random variables. We're actually dealing with X bar, not X. So let's go back down to our formulas that we need to use. And this is all related because we need to calculate this Z score. We have the standard error already calculated, square root, or I should say, standard deviation of the population, and we have that divided by square root n. We have this calculated. What we need to calculate are these values, X bar minus mu, and so forth. So that's how we would actually calculate Z. So we have several different cases we can consider, and the Excel formula over here is based on which case we're actually talking about. Our question is find the probability of getting a sample between two different values, one a lower bound and one an upper bound. That's why these figures are important to consider. Now these are generic figures. We have one case where it's less than. Right now I stuck the shaded region from negative infinity to -1. Just as easily could have been negative infinity to +1 or 2. So it just represents the case where we're trying to find a probability of less than something. We also have the greater than case. So find the probability or the area of the shade in region that is greater than a specific value. And of course this is normalized to the z or t distribution. We have two more cases. Find the probability being between two values, which is exactly what we want in our particular problem. And then the fourth, which is the least likely that you'll ever see, is find the probability of being outside of this region, which essentially means you're an outlier. You're either on the right tail or the left tail. Okay, so we are definitely talking about C, so we can refer to these equations, and we can go ahead and copy this, if you will, from the formula sheet just so we know. And we're going to write this statement: what is the probability of x bar, the x bar we care about, being between x1 and x2? So I'm going to minimize this. We have our x bar 1, x bar 2, and we're trying to find the probability x bar 1 is less than x bar less than x bar 2. And the formula that we're going to use, I'd just recommend pasting that into the cell. And if you do, it's going to be on two separate lines, so it might be confusing when you look right here. If you pull this formula bar down, you're going to see the remaining part. So let's go ahead and delete this so that the formula is on one line. Now you'll see what we need to do to calculate this is to provide a z value based on x2 and a z value based on x1. So we need to calculate those. For right now, I'm simply going to put a quotation mark, which turns all this into text, static text, versus a formula. So I'm going to leave that there for now. And I'm going to drag this down a little bit, both of these cells, so I can calculate z x bar 1 and z x bar 2. Okay, and now I'll actually move this to another row down and provide some formatting here. Okay, so let's calculate the z of x bar 1 first. We have the difference between 477 minus our mu divided by our standard error, which is calculated in part A. I'm going to go ahead and put dollar signs on the standard error and the mu, just in case we want to reutilize this this formula. We have a standardized score of negative 1.9. Let's calculate the positive side, which I know it's positive because 527 is greater than the average, the center of the distribution. So let's go ahead and calculate that. We have parenthesis 527 minus 502, and I'm going to put dollar signs on that again, divided by the standard error of 12.9, and I'm going to put dollar signs on that. So it happens to be that these are equally distributed away from the center. So in other words, our center is 502. These happen to be equal distances away in magnitude away from that center. In other words, if I took the difference 502 minus 477, we get 25. And if I take the difference 527 minus 502, we get 25 as well. So it makes sense that we're seeing standardized scores that are equal in magnitude. These are the little checks you got to run in your head to assess the problem. I knew this was going to be a negative z-score because it's to the left of our mean. 477 is less than 502. And I knew this would be positive because 527 is greater than 502. So if you didn't know which way to do this difference, maybe you're confused and said, okay, I need a z for x bar 2, and I'm going to take 502 minus 527. Well, that's going to be a negative value. So we know it's positive, and once you identify the positive or negative sign, you can take the difference correctly. And then all you have to do is calculate that standard error to get your z's. Okay, so with that said, let's go ahead and go down to the normal.s formula. I'm going to take out that single quote, and all I'm going to do is reference z of x2, which is 1.9, and zx1, which is here. Hit enter. Our probability of obtaining a sample with a mean between these two ranges is 94%. And that makes sense since our plus and minus range is about 2. So using the empirical rule, one standard deviation away from the mean is about 68%. 2 standard deviations is a probability of about 95. And if we go to 3 standard deviations, plus and minus 3, we're looking at about 99% of the area under the curve. Okay, I'm going to provide just a little format. I think it looks better. Let's go ahead and why not apply yellow with bold. And I'm going to go ahead and use autocorrect. Okay, moving on to C, calculate the likelihood that the sample mean is between these two values. Okay, we could go through the same exact process as we did here. What I'd like to do is reuse code, and I'm going to paste that here. So I'm going to change B to C. My new x bar 1, I should say, is 492. My new x bar 2 is 512. That means I get different standard deviations, or I should say different standardized scores here, negative and positive 0.77, and then my calculation for my probability is already determined. So it just happened to be in the same form. Both of these are in terms of knowing that they are between, so they are the same formula. Okay, the final part, what probability is the sample mean likely to be greater than 550? Okay, we have sort of a different probability question here. In this case, for part D, we have a x bar 1 of 550. We need to calculate the z x bar 1. And you should be asking yourself, well, is this going to be positive or negative at this point? This value should be positive because it is greater than the 502 mean. So I know to calculate the z bar, it's going to be 550 minus 502 divided by the standard error of 12.91. Now I recommend putting these dollar signs in just in case you ever want to reutilize this code. We can calculate other probabilities. Okay, so the probability now, or the challenge to us now, is identifying which case this is, so we apply the right probability. We want to find the probability of x bar being greater than, we'll call it x bar 1. So let's go ahead and take a look at that, just applying some general formatting here before we look at the formula sheet. So we know we're in a situation where it's greater, so we're talking about case B. We already made up our mind that we're talking about the z distribution instead of the t. So we need to look at this row of the data set. So what is the probability of x bar being greater than this value of 550? We can copy that formula over. Essentially, we have 1 minus norm.dist. What this is actually doing is saying, okay, I'm going to supply a z value here. And if we look at the formula here, what it's actually doing is going to calculate all of this unshaded area. And then to calculate the shaded in region, all we're doing is saying, I know that 100% of the area is under the entire curve. So 1, in other words, 100% minus this unshaded part is exactly the black. So let's go ahead and go back to our spreadsheet, and I'm going to paste this in, and all we have to do is reference the right z-value. The z-value is 3.7. So we have a probability of 0.01%. Very, very low. And we can tell that based on the z-bar. The z-bar is 3.7 standard deviations away from the mean. That means if we have a distribution, let's look at it here. If we have a distribution like this, we know that 98%, basically 99% of the distribution's area is in between plus and minus 3. We're asking, well, we're way out here at 3.7, which is, let's just call it here. What's the probability of getting something from 3.7 to positive infinity? We're so far away out on a tail, that zero, or that probability is essentially zero. So my recommendation when you go through some of these calculations, you really got to think where you are on the distribution and do these values make sense. And it's really helpful if you study this table and understand why these Excel formulas are the way they are.